our final part here is to take a look at limits at infinity, and specifically what happens if we aren't looking at an x value kind of in the domain in the center of the graph that we're looking at, but what happens when x goes all the way out to the left-hand side or the right-hand sides of our graph. So what happens as x approaches an infinity? What part of a coordinate plane or graph is x approaches infinity? If you take a look at the coordinate plane that I have here, if we talk about x going towards infinity, we're talking about all the way out here. This arrow, basically, essentially, is what we're looking at. As x heads way out to the right, this is x approaching infinity. Or if you want to talk about x approaching negative infinity, that's all the way over here on the left-hand side. Again, I'm not going to say x equals infinity because we can never be equal to infinity, but we can head towards that. That's where we're going to use the little arrow for approaches. We're heading towards that infinity. So on the coordinate plane, when we talk about x approaching one of these infinities, we're talking about kind of what happens if the graph could extend and kind of where is the graph going to head towards. Limits are all about patterns. So if we're talking about what happens and what kind of pattern is the function following if you keep going beyond the coordinate plane, you're basically talking about an end behavior of a graph. Now, in pre-calculus or in Algebra 2/Pre-Calc, you would have talked about kind of the different end behaviors for certain graphs. For polynomial functions, to compare a polynomial function, you'd look at the degree and the leading coefficient to kind of determine what the end behaviors were doing, which end behavior was pointing in which direction. For rational functions, you're basically looking at horizontal asymptotes. Those were the most common types of end behaviors you saw with rational functions. And we have this wonderful mnemonic device that you may not have seen before. It's BOBO, eats DC, bot none. I'll go over what that means in a couple of examples. You have exponential functions. With exponential functions, one side had a horizontal asymptote, the other side went up either to positive infinity or down to negative infinity, depending on the structure of your equation that you're working with. So you had one horizontal asymptote and one kind of infinite end behavior to work with. And for your basic trig functions, you don't really have a set end behavior because it's periodic. You can kind of predict what the function's going to do, but it's not really heading towards one y value. The sine function continually bounces between +1 and -1. It doesn't go to one specific y value, it just continues to rotate between those two values. So there's not really a set end behavior for those ones. So you're not really going to see these come up too much with the functions that we're going to be working with in terms of limits at infinity. So one thing just to remember for this is that the end behavior you have on the right-hand side may not be the same as your left end behavior. Exponential functions are a classic example of this, but it does sometimes show up with rational functions as well, so just kind of be aware of that. It definitely also can happen a lot with polynomials, but rational functions and exponential functions, please be aware that those sometimes don't always have the same end behavior on both sides. So we're going to evaluate the following limits. The limit as x approaches infinity of this polynomial expression here. Since we're talking about infinity, I technically don't plug in infinity, although you can think about it that way. You can think about what happens when I plug in a really large number. But when it comes to polynomials, you want to look at two different items as your shortcut. Your degree, which in this case is 3, and the leading coefficient, which in this case is a -2. Since your degree is odd and your leading coefficient is negative, that means that your leading coefficient being negative means the right-hand side points down. The odd degree means that the left-hand side will point in the opposite direction or up. So for this function, no matter what it does, it's not quite as detailed as that because it's only cubic, but this is kind of the general shape of what's going on with this polynomial function. So if we're approaching x is approaching positive infinity, that's talking about the right-hand side, we can see that this is approaching negative infinity. So what I'm going to do is say that this limit is equal to negative infinity. So technically it doesn't exist, but we're going to include a negative infinity in there to kind of describe the fact that it's heading down in our graph. For the next one, we have a rational function, and this is where we're going to go over that Bobo eats DC kind of thing that's going on here. So we have the limit as x approaches infinity of this rational function. When it comes to rational functions and determining horizontal asymptotes, there is this mnemonic device that is out there that you may not have heard before, and it's Bobo eats DC and but none. So Bobo is if your exponent is bigger on the bottom, your horizontal asymptote would be 0. So having a degree bigger on the bottom automatically means that the x-axis, or y equals 0, is going to be where your horizontal asymptote will be for both sides. For eats DC, it means that if your exponents are the same, hence eats, you're going to divide the coefficients. So look for those leading terms, look for your degrees that match up, and divide those coefficients with each other, and that's going to give you what the horizontal asymptote will be, again, on both sides. The last one is bigger on top, so that's but, and then there's none. If you are bigger on the top, it means that you do not have a horizontal asymptote. You might have an oblique asymptote, which is something that you may have heard of before. It happens in a very specific case, but even with oblique asymptotes, your end behaviors are either going to go towards a positive infinity or a negative infinity. With the oblique asymptotes, it follows a specific linear pattern, but it's still going to have positive or negative infinity in terms of the limit, which is what we're looking for here. So that is the Bobo eats DC and but none mnemonic device to help kind of remember what happens with rational functions. So in this first one here, we're going to look for our degree on the top and the degree on the bottom. Your degree on the top is a degree of 4. The degree on the bottom is a degree 8. So because we are bigger on the bottom, it means that we have 0. Your horizontal asymptote is 0, and so therefore your limit is going to be 0. For our next one here, we're going to find out that we have a degree of 2 on the top, also a degree of 2 on the bottom. So all I'm going to do is divide those coefficients. -7 over 5, so we're going to have -7/5. That's going to be our limit value. That is the y value that this function is heading towards as x gets larger and larger and larger. We're heading towards -7/5. Do we actually get there? No, but that's where we're headed. And that's really what the limit's talking about. Where are you going? What's the pattern? What's the direction you're heading in? Last example here, we have x to the 4th on the top and x to the 3rd on the bottom. So we are bigger on the top, which means there is no horizontal asymptote, which means we are approaching an infinity. And for limits, we have to figure out which infinity we're heading towards. And this involves a little bit of work with some negative numbers and kind of dealing with what happens in the function. So let's consider we're heading towards negative infinity. So we're plugging in a really large negative number. So 3 times a really large negative number to the 4th, added with 7 times a really large number, all over 5 times a really large number, I keep writing 1, really large number to the 3rd, 8 times a really large number, plus 73. If you're thinking about a really large number, in all honesty, guys, the last couple terms in here really don't count. Because a really large number to the 4th and a really large number to the 3rd is really going to dictate what happens here. The rest of it, it's just not enough to really compare. So 3 times a really large number to the 4th is going to be a positive value. 5 times a negative really large number to the 3rd is going to end up being a negative value. So a positive value over a negative value is going to end up heading towards a negative infinity. So we knew that this one was going to head towards infinity because we had an exponent that was bigger on the top, but we weren't sure which infinity it was approaching. All of this work really in here is just to try to figure out, would we end up with negative values or positive values? And in this case, we ended up with a negative value. So that is our discussion on limits. You are now ready to tackle all of the problems in our Delta Math summer assignment. If you continue to have more questions about anything that you've seen on these different instructional videos, or if they're just not working for you, please give me an email and I will try to respond back as soon as I can.